Good afternoon, everyone. This is Professor Kuehn, and today I'm going to give a short introduction to the laboratory exercise for this week. This week we'll be doing exercise 20.3 in a student's guide to the grade physics text. This is the force and rotation laboratory. So what I'm going to do is I'm going to prepare, along with Professor Schindler, a few videos that will help you get through this laboratory. In this video, I'll give a brief introduction to some of the background ideas that you're going to need to employ in order to understand this laboratory. And then there's going to be a few short videos where Professor Schindler and I are going to be doing some experiments in the laboratory. And what you all will need to do is watch all of these videos, and we'll be shouting out some data that you guys can collect in your lab books, and that will help you in your analysis. Okay, so what I want to do right now is I'm going to turn off the webcam and draw some diagrams that explain what we're going to be doing in this lab. So I'm going to turn off the webcam, and you should be able to see my screen now. And so here is the idea. I need to give you some background on Newton's laws of motion that will help you get through this lab. I'll probably explain these in a bit more detail in an upcoming lecture, but here you go. So what are Newton's laws of motion? So Newton's three, he calls them his axioms. We now call them his laws of motion. The first law of motion says that essentially every object that is at rest tends to stay at rest, and objects in motion tend to stay in motion at a constant speed in a straight line. So this is sometimes called the principle of inertia. Newton did not come up with this law, but it got absorbed into what is now known as his first law of motion. So the principle of inertia, which is objects tend to retain their state of motion or rest. So an object at rest stays at rest, an object in motion stays in motion. This basically tells us what happens when there is no force acting on a body. When no force acts on a body, this is what happens. The second law of motion says that when an object feels a force, its motion changes. So an object experiencing I should be careful here, a net force, by that we mean an unbalanced force, experiences a change in its state of motion. Newton would call it its quantity of motion. So Newton calls this its quantity of motion. And we would call quantity of motion, nowadays we call this momentum. So let me mention really quick how we define momentum. So this is an aside. Momentum, an object's momentum, is equal to its mass times its velocity. So if we know the mass of an object, let's say something is moving, something has a mass of 3 kilograms, and it's moving at a speed of 10 meters per second, its momentum will be 30 kilograms meters per second. Okay, so that's how momentum is defined, as mass times velocity. So what this is saying is that when there's an unbalanced force, its momentum changes. Okay, so there's a few ways that this could happen. So for example, let's suppose that you have a hockey puck and it's on the ice like this. And let's suppose that initially it has a speed or velocity in this direction. Well, what happens when we apply a force to it? There's really 3 ways. I'm going to look at a top view. Let's suppose this is a top view. We've got its velocity this way. That's its speed. And let's suppose we hit it from the back with a hockey stick. So we apply a force to the back. Well, its initial momentum, let me actually change this and say its momentum is in that direction. I know momentum is related to velocity, but let's, just to be clear here, its momentum is in this direction. So because it has a mass of 3 kilograms and a speed of 10 meters per second, let's say its momentum is in this direction. What's going to happen is it's going to speed up. And so the force causes the momentum to increase, right? So there's going to be a change in momentum. That is, it's the final momentum after the force is applied. The final momentum is going to be bigger than the initial momentum. Okay, well, alternatively, if its momentum, that would be kind of case 1. Alternatively, if its momentum is going this way and we hit it in the front with this force, like this, what's going to happen? Well, its momentum is going to decrease. So in this case, if the force is in the opposite direction of the momentum, the force is going to cause the momentum to decrease. Right? So it's going to slow down. In other words, the final momentum is going to be less than the initial momentum. Right? That's case 2. And case 3, let's suppose once again the hockey puck is moving with the momentum in that direction. Well, maybe we don't apply the force to the back or to the front. Maybe apply the force to the side. We just kind of slap it on the side with the hockey stick as it's going past. Well, in this case, the force does not cause the momentum to increase or decrease. Rather, the force causes the momentum to change direction. So whereas initially, so I'm going to draw another little picture, the initial momentum, let me call it this. This is the initial momentum. I'll draw it with an arrow like that way. That's the initial momentum is that way. Afterwards, its final momentum might be downward a little bit, right? So it was sliding in this direction. You hit it on the side with the hockey stick, and as a result, its final momentum is kind of directed downward. The size of the momentum, maybe it's still going at 30, has a momentum of 30 kilograms meters per second initially. It could have a final momentum of 30 kilograms meters per second, but it's in a different direction, okay? So the final momentum, at least in its size, the final momentum is equal to the initial momentum, at least in magnitude, but is in a different direction. That counts as a change in momentum, by the way. All right, so these are kind of 3 classes of changes of momentum one can have: an increase in momentum in case 1, a decrease in momentum of case 2, and a change in the direction of momentum case 3. Of course, you can have kind of combinations of these. So for example, if you hit this puck kind of behind it, but in a kind of funny direction, you might speed it up and change its direction, okay? So this is all related to Newton's second law. By the way, there's a formula that relates the change in momentum. Delta P is the final momentum minus the initial momentum, right? And we can relate that change in momentum to the force and the time interval during which that force is being applied. So for example, if I apply a force in case 1, let's suppose I apply a force of 1 Newton, and I apply that for 1 second, the change in momentum is going to be 1 Newton second. Okay, and if you work it out, that ends up having the same units of kilograms meters per second. So it's going to increase, its change momentum is going to be positive, its final momentum is going to be bigger than its initial momentum, and the amount that it increases by is the product of the force and the time during which this force is applied. Okay, so let me pause there for a moment because I'm out of space, and then what I'll do is I will come back and continue by describing Newton's third law of motion.